Welcome back to our Chem 152 video series. Today we'll be dealing with cubic structures and the density of cubic structures. This presentation contains diagrams provided by OpenStax. In this problem, we'll be looking at tungsten. Tungsten crystallizes in a body-centered cubic unit cell with an atomic radius of about 1.37 angstrom. The problem asks us to find the density of tungsten. But before we begin, let's talk for a moment about body-centered cubic cells. This diagram shows information about the three main types of cubic unit cells you'll need to know for Chem 152. Showing simple, which contains an atom on each corner of the cell, body-centered, which has red atoms on the corners and one blue atom in the middle, and then face-centered, which contains red atoms on each corner and 6 blue atoms, one on each face of the cube. Now, if you look at the diagram first for simple cubic, you may think that there are 8 atoms inside of this cube, but atoms on the corner are only 1/8 of the way inside of the cube. So if we are to look at the number of atoms inside of this unit cell, we'll note that there are 8 atoms, but all of them are corners. So we'll say 8 multiplied by 1/8, which is how much of the red atom is inside of this cube. If we take 8 times 1/8, we'll get 1 atom. This tells us that for a simple cubic structure, there's actually only 1 atom in the cube, even though it looks like 8. If we look at a body-centered cubic, notice there is a red atom on each corner and a blue atom in the middle. We already know that the corners count for 1/8, and we'll take 8 times 1/8 for that. The one in the center counts normally. We'll make no modifications to the center atom at all, and we'll just add an additional +1. So 8 times 1/8 gives us 1, plus an additional 1, meaning that there are actually 2 atoms inside of a body-centered structure. This will be the case even though it looks like a total of 9 atoms. It's really only 2. Next, we'll look at face-centered cubic structures. The red atoms are on the corners. We know there are 8 of them, and each of them counts for 1/8. The blue atoms are on the faces, though. Each atom on the face counts as 1/2. With half of the atom being inside the cube and half being outside. However, we have 6 faces on a face-centered cubic. We'll take 6 times 1/2. This will give us 1 from the corners, that's 8 times 1/8, and then 6 times 1/2 gives 3, add them together, giving us 4 atoms in a face-centered cubic structure, even though it looks like a lot more. Also, each type of cubic structure has a different formula for edge length. Simple cubics have an edge length of 2 times r. Body-centered cubics have an edge length of 4 divided by √3 times r. And face-centered cubics have an edge length of 2 times square root 2 times r. Now, our structure had body-centered, so the only information that's relevant to this problem is the body-centered information. Because the problem said that our structure is body-centered, we know that our structure will have 2 atoms and will have an edge length of 4 divided by √3 times r. Now that we've gathered this information, let's remind ourselves that our goal is to find the density of this tungsten. So let's remind ourselves of the meaning of density. Now, density is usually represented with the Greek letter rho, which is this strange-looking P, and it's divided by mass divided by volume. The mass must be in grams, and the volume must be in centimeters cubed. Now, as it stands, we don't know the mass, and we don't know the volume, and we can think of this process as having 2 parts. First part of this process, which we'll label part A, is going to be to find the mass inside of this unit cell. Part B will be to find the volume. Let's start with part A and find the mass. We don't have a lot of information to go on, but we do know two things. We know there are two atoms inside the unit cell, and we also know that the atoms in question are tungsten. So what we'll do for part A is do a conversion. We will change the atoms to moles first. Generally, the cardinal rule in chemistry is if you don't know what to do, try going to moles first. And then we can go from moles to grams. So we will have two steps for a double conversion. First, we'll go from atoms to moles, write down the two atoms we start with, and multiply by a fraction. That will take us out of atoms, which we place on the bottom, and moles on the top. Now, recall that moles to atoms is a conversion that uses Avogadro's number. And Avogadro's number tells us that 1 mole is the same thing as 6.02 times 10 to the 23rd atoms. Therefore, we place 1 on the top and 6.02 times 10 to the 23rd on the bottom. After that, our second conversion is going to be to go from moles to grams. We'll take the moles from the top of the first fraction, move it to the bottom of the next fraction, and remind ourselves that our goal is to go to grams. So for our second step, moles to grams is going to be molar mass, which is something we can look up on the periodic table. At this point, you may wish to press pause and open your periodic table to locate tungsten. The periodic table gives tungsten's molar mass as 183.84 AMU. Therefore, we'll place 183.84 next to grams and place 1 for moles. Now, we'll need to enter this series of fractions into your calculator. For those of you using a TI-36X Pro, which is standard for Wake Tech's Chem 152 class, I recommend that you change your mode to scientific notation at this time. To change your mode to scientific notation, locate the mode button on your calculator, press it, and then navigate on the screen to where it says SCI and press enter on that region. This will change you to scientific notation. Trying to use standard general notation for these sorts of problems can lead to rounding errors. After doing that, enter these calculations into your calculator. 2 divided by 6.02 times 10 to the 23rd, multiplied by 183.84. You can expect to get a very small answer. If we round this to 3 significant figures, we'll get 6.11 times 10 to the negative 22nd power grams as our answer for part A. Now that we know our answer to part A, and we have that the mass is 6.11 times 10 to the negative 22nd, our part B is going to be to get the volume of the unit cell and change it to cubic centimeters. Now, we're not given the volume for this problem, but instead what we have is the atomic radius, and this formula that the edge length is equal to 4 divided by square root 3 times that radius. Let's begin by placing the 1.37 in place of the r to get the edge length. We'll say that L is 4 divided by square root 3 times 1.37 angstrom. We abbreviate angstrom with an A and a circle over it. We'll place this operation into the calculator. After placing this in the calculator, we get an answer saying our edge length is 3.16 angstrom. However, that edge length is in the wrong units. We will need to change the edge length to centimeters in order to get it into the proper units to where we can find the volume. So we'll change the angstroms first to meters and then change from meters to centimeters, and so we have another two-step conversion. We'll begin by bringing down the angstroms we just found, 3.16. We're going to multiply it by a fraction where we'll get rid of the angstroms by placing it on the bottom, and we'll go to meters, which we place on top. 1 meter is the same thing as 1 times 10 to the 10th angstrom. However, we'll have to multiply by another fraction to get to centimeters. Therefore, we'll take the meters from our first fraction, move it to the bottom of the next fraction, and remind ourselves that our goal is to get centimeters as our final answer. Now think about your SI units at this point. 1 meter is the same as 100 centimeters, and so we'll enter this multiplication chain into our calculators. We'll have 3.16 divide by 1 times 10 to the 10th, multiply by 100. We'll have an answer of 3.16 e negative 8, and our unit will now be centimeters. The third step to this process, now that we know the centimeters, we'll get the volume. The formula for volume is going to equal the edge length raised to the third power, and this will be true for any cube. Therefore, we'll say volume is equal to 3.16 times 10 to the negative 8, put it in parentheses, and raised to the third power. Therefore, our volume is now 3.17 times 10 to the negative 23rd power, and the units will be centimeters to the third power. This is because we previously had centimeters inside. When we raise the centimeters to the third power, we'll get centimeters cubed. Now that we have our mass from part A and our volume from part B, all that's left to do is divide them. If we round our answer to 3 significant figures, we'll have 19.3 grams per cubic centimeter as our answer. Once again, make sure that you do these calculations only in scientific notation, because it's possible to have a round-off error if you don't. Thank you very much for watching. We'll see you again soon.